Welcome back to our exploration on magnetism. Last time we covered the basics of how charged particles move in magnetic fields and discussed the Lorentz force. Today we will continue by examining the motion of charges in magnetic fields, and we will introduce a practical application of these principles, the velocity selector. Before we proceed, let's revisit the Lorentz force equation. So the force F on a charge Q moving with velocity v in a magnetic field B is given by the expression F is equal to Q v cross product B. This means the force is perpendicular to both the velocity and the magnetic field. The magnitude of the force can be expressed as the force is equal to QVB sine of theta, where theta is the angle between the velocity vector and the magnetic field vector. Since we are dealing with three-dimensional motion, it's important to understand how to represent vectors pointing in and out of the plane of the board, the screen, the paper. An arrow pointing out of the board will be represented by a dot. Imagine it is the tip of an arrow coming towards you, like looking directly at the tip of an arrow head. An arrow pointing out of the board would be represented by a cross. This resembles the tail of an arrow going away from you, as if you are seeing the tail end of the arrow. This notation helps in visualizing the interactions between the velocity, magnetic fields, and the forces in our diagrams. So, let's focus on motion of charges in magnetic fields. Let's look at how the Lorentz force affects the motion of a charged particle based on the direction of its velocity relative to the magnetic field. For example, the motion, if it's perpendicular to the magnetic field, then theta is going to be 90 degrees, sine of theta is 1. And when a charged particle's velocity v is perpendicular to the magnetic field B, the force F is perpendicular to both the velocity v and the magnetic field B, resulting in a circular motion. The particle follows a circular path because the magnetic force acts as a centripetal force to the velocity, which is tangential. And the radius of curvature, as we saw in the previous lesson, is mv divided by qb, where m is the mass of the particle, v is its speed, and q is the charge, and b is the magnetic field strength. Now, let's look at another example. Let's assume that the motion is parallel to the magnetic field, then theta is 0. So the sine of 0 is 0, so if the velocity v is parallel to the magnetic field b, then the magnetic force is 0. The particle will continue in a straight line at a constant speed. Let's think about somewhere in between, a motion at an angle theta to the magnetic field being theta between 0 and 90. If the velocity makes an angle theta, then the particle experiences a combination of circular and linear motion, resulting in a helical path. We can use this to build a velocity selector. Let's think about this device. This is an important application used to filter charged particles so that only those with a specific velocity pass through the device. So how does a velocity selector work? A velocity selector is a device that uses both electric and magnetic fields to allow only particles with a certain velocity to pass through. It relies on the balance of the electric force and the magnetic force. A uniform electric field, E, is applied in a particular direction, and the uniform magnetic field, B, is applied perpendicular to the electric field. Now, charged particles, like electrons or protons, enter the device with velocity v. The forces acting on the particle will be the electric force on the particle, which is given by F sub E is equals to Q times E. And then we also have the magnetic force, which will be given by QVB. So we have these two forces acting on the particle. The two forces act in opposite directions. The condition for no net force is that if the forces are equal in magnitude but opposite in direction, they will cancel each other out, and the particle will move straight without being deflected. Now, if they are not equal, if QE is not equal to QVB, then there will be some net force pointing one way or another way, and the particles will be deflected. So only particles with the velocity v equals to E over b will pass straight through the device without being deflected. Particles with a different velocity will be just pushed out of the path due to the net force acting on them. Some applications of this, well, the mass spectrometry. The velocity selectors are used to separate ions of different masses which have been given a specific velocity to analyze the mass to charge ratios. Can you think of how this would be done? Then we also have particle accelerators that they help filter out particles with specific speeds to study particle interactions. Can also be used as isotope separation. Velocity selectors can assist in isolating particular isotopes by selecting ions with precise velocities. To sum up, charged particles experience a force when moving through magnetic fields, leading to circular, elliptical, or even linear motion, depending on the orientation of the velocity relative to the field. The velocity selector uses both electric and magnetic fields to filter particles so that only those with a specific velocity pass through. This works by balancing the electric and magnetic forces. Applications of the velocity selector range from scientific research to industrial processes, demonstrating the practical use of understanding electromagnetic interactions. We will see more applications in coming lessons. For example, in our next lesson, we will discuss magnetic forces on current carrying conductors and introduce the concept of torque on a loop, setting the stage for the understanding of the electric motors. Feel free to reach out with any questions, and may science be with you.